a lecture on phenomenology, really. So after having seen so many theoretical properties and constraints that we can put on the standard model Higgs, we are now going to look at searches, right? So what is being done to find or exclude this particle. So here is the outline of my lecture. So first of all, we will look at how it is produced at Hadron Collider. So clearly the Higgs boson physics these days is Hadron Collider physics. So how a standard model Higgs boson is produced at Hadron Colliders. And our focus will be again on the standard model Higgs, and the reason should be clear from lecture number 1. So just because we're now the game is really on. And we really need to understand how to do a really precise job and a really good job. And it doesn't pay to look at a generic search for many different situations. Just look at one situation and do it well. And then when you can do that well, then you can do anything else. So we will look then at results from the Tevatron and results from the LHC and how Higgs physics and what the Higgs program looks like at both machines. And then we will start to delve into the real job that the theorists should do. So we first want to look at the generic structure of a hadronic process and try to break it down into building blocks that we need to have under control. And then we try to answer this fundamental question of how a theorist can do a good job. You're going to have experimental talks from both Atlas and CMS. So I'm not going to review each single search channel, not at all, right? So I'm going to give you the big picture, but then I'm going to try to discuss with you what should you do as a theorist, so on the theory side, in order to be able to compare with the data that are coming online and that are already online from the Tevatron. So it will be a matter of understanding the hadronic environment, and from that point of view, you need to understand QCD really well. And you're going to have lectures on QCD from John Campbell, and he's going to discuss much more than I can do this morning. And we'll then try to, the second important thing is just to understand the experimental measurement. That's probably even more difficult. So sometimes it's really difficult to really have clear what is done experimentally. But it's really important if you want to have the right theoretical prediction. And then we come to understand the systematic of the theoretical errors. And that's really important on the theoretical side. So really what the theorists should do, to try to understand it systematically in such a way that you have it under control. So you know at which level you are and you know what you're missing. In order to give to this discussion a little bit more of content and to flesh it out a little bit more, I will use an example, which is the example of the main production mode for a Higgs boson, so gluon-gluon fusion, just because I think that so much has been done on this mode, and this mode is so particular that it's almost a tutorial in what you should do in order to really have a production mode under control theoretically. And so we end up with an overview of what is being done these days and what has been recently achieved and what the studies are ongoing right now. And of course, the final disclaimer on what we haven't discussed so that you don't think that I forgot about it, just had to prioritize things. So here is just to have the picture in your mind. All the curves that you will see in the future plots, they all refer to these fundamental production modes that you divide into the main production mode, which is gluon-gluon fusions, and you say, wow, it's already a loop production mode, which is the mirror image of the decay that we have discussed in one of the previous lectures. But because of its 2-to-1 structure and because of the top loop, has a very large cross-section. Then we have what we call weak boson fusion, so vector boson fusion production which is a weak production mode in a way. It's a weak coupling of the Higgs here. And then we have the associated production with the W and Z, and the associated production with heavy quarks, so top and bottoms. Now, in the standard model, you consider these three main modes, and you consider the production with the top. The production with the bottom is very much suppressed because of the Yukawa coupling of the bottom. I put it here as well because it is important. It's an important production mode as soon as you go beyond the standard model with an enhanced bottom coupling. So you see it in results very often. It is already sort of stringent constraints have already been placed, for instance, in some version of the MSSM for not having seen it. So the Higgs programs at the Tevatron in a nutshell, so in one transparency. First of all, let's focus on the plots here on the left-hand side and try to understand how we can tell without even knowing how Higgs physics is going to be done at a given machine. So here you have all the production modes that were drawn in Feynman diagrams in the previous transparencies. So gluon fusion, associated production with a W and a Z, the weak boson fusion, and the associated production with heavy quarks. Now, in order to determine how you're going to look for, you need to consider both the production and the decay. Right? So now you look at that's why here I sort of underimposed here, I just plot these two, I give you these two plots together. And I give these two plots together. Of course, here it's the range of masses is different. This is only from 80 to 200 because you have to think that the tevatron cannot go much higher than that. And I use the same branching ratio plot that I will use also for the LHC. So for this particular plot, you don't have to look at it one by one, but you have to limit yourself to up to here in terms of branching ratios. So for the tevatron, what is let's look at the branching ratio plots to start with. Well, there is a big difference if you look at low masses, so masses below, let's say, 130, 140 GeV, before the WW and ZZ decays kick in, and the region above that, where they dominate. So for the tevatron, this will be basically putting a line more or less at this level, so around 130, 140 GeV. And the physics that you would do and the choices that you will make depend on that line. So depend if you are in the region of a light Higgs or in the region of a heavier Higgs. So a Higgs that can decay into WW and ZZ or a Higgs that cannot decay into that. So for the tevatron, therefore, you have, so for the tevatron and for the LHC, you will have to combine production and decay to figure out what your best option is. So for the tevatron, what turns out to be is just that if you are in the low mass region where the Higgs decays, the standard model Higgs decays mainly into BB bar, gluon-gluon fusion is not an option in that particular region because of the fact that there is too low statistics to handle that the larger hadronic background that you would have for a model that is produced via gluon-gluon fusion, so with a lot of hadronic activity, and decay into jets, so decayed into 2Bs, right? So you don't use that in the low mass region, but you use in the low mass region the associated production with the W or a Higgs, with the Higgs decaying into BB bar. Now in the higher mass region, the tevatron goes above 130, 140 GeV up more or less to 180, 200 GeV, you can go back to gluon-gluon fusion, and you can use gluon-gluon fusion now, which is still largely produced in that region, paired this time to a decay that is starting in that region and ramping up, which is the WW, and is less prone to background than the BB bar decay is. So using these two main modes, although if you read the paper that has produced this exclusion plot, other modes have been used as well, but those are the two leading modes in the two regions. The tevatron has been able to come up with this plot that you have already seen many, many times, in which you plot the confidence limit of your measurement, so the sigma of your measurement over the sigma in the standard model. So the standard model would be correspond to the line at 1 in this plot, as expected and as observed with the statistical error at 1 sigma in the green band and the 2 sigma at 2 bands. And whenever the curve to start with the dashed line, which is the expected, and now that we have data, the observed one goes below this line, you can say that you have excluded the standard model. Yes?
So there's been some discussion about the error limits for the...
Yeah, let me come to that. Okay. Give me time to talk. Okay. So this is precisely the plot that, if you look at the number, gives you the limit, the exclusion limit between 158 and 173 in this plot. So having this exclusion limit is very important. It's a dramatic result, as a matter of fact, because it's going to be verified again by the LHC, but at the same time it gives indication. So it gives indication to the LHC people where the effort should go and what the tevatron has already seen. So it's really important that this result is cast onto a very solid ground. And I will come to the discussion of your question when we get to discuss what goes into the prediction in the theoretical prediction in particular. So when we, I'm sure that this will be discussed even more at length in the ATLAS and CMS. Well, on the experiment, I don't know if we have a talk on the tevatron, if anybody's going to talk about the tevatron, experimental talk on the tevatron. But in any case, similar plots will be discussed also by ATLAS and CMS. So when we come to the LHC, I want to summarize for you the program of the LHC, the Higgs program for the LHC. Here are the very same two plots. So the bottom one, well, not the very same. The bottom one is the very same plot. The upper one that now goes over the same mass range because the LHC the LHC can explore the entire mass range, has the cross-section, of course, for the LHC. Now, these are plots that were done with, I used just plots that I have that were done with PDFs that are now outdated, but this is not the point for these plots. I will show to you later on very much updated plots on the same thing. This is just to understand the messages. It's just to understand how you proceed. So here you see the same productions mode. Of course, the curves will look different if you compare to the one of the Tevatron because it's a different machine. It's a PP machine. It's a PP bar machine. The energy is different and so on and so forth. So, but you play exactly the same game with the difference that now here you go over the entire mass range of the Higgs, and you have much more energy, so you have more statistics, so you can allow yourself to explore more things. So again, you divide the whole discussion into low mass region, which is basically over here, and the high mass region. And in the high mass region, let's look at that first. As you notice, you use basically all the production modes, mainly with the Higgs decay into WWs and ZZ, because those decays are very clean to identify in a hadronic environment. So you want to use them as soon as you have them. And of course, also gamma gamma is a very clean decay, and you can still use it, but it's very, very small. If you look at this plot, for these kind of masses above 130, 140 GeV, it goes a little bit, and then it's not even plotted anymore because it's really small compared to the other decay branching ratios. When you get to the low mass region, which is the most cumbersome one, and unfortunately also the most interesting one, if you really wanted to disprove the standard model Higgs bosons, and you think that it is consistent with the electroweak precision fits that we have seen yesterday, well, you may want to use everything you can, including if you push really to the limit of 140, also the WW and this ZZ decay, but definitely you need to use also BB bar that is large in this region. And you can use it, however, it's still a very hard life, definitely, to use it for gluon-gluon fusion, and it's not being used for that. It has not even been used for weak boson fusion. It has been, when I say used, it means that there are analyses that have studied this a given production mode with a given decay mode. And these analyses exist for the associated productions. So for the associated production with Ws and for the associated production with TT bar, as well as analysis that on top of BB bar also use gamma gamma when you go to high statistics, because of course you need high luminosities in order to use a decay that has a very, very tiny branching ratio compared to the BB bar one. But that can be very clean, so you can compensate that factor by cleanness and less background that you have. So this is the program of the LHC. Low mass region, high mass region. Analysis exists for all these processes. They have been updated more and more. And those are the ones that are used or will be used in the program that the LHC will present us. And the LHC Higgs program has started. And has started really well. So we know that the energy now is 7 TeV, so we needed to take those plots, rescale them down to 7 TeV, and see what we can do with 7 TeV. But at the same time, from when those plots were done originally and when the study on Higgs physics has started to become more concrete, like 10, 15 years ago, a lot has been done in order to also refine the kind of analysis that can be done and the kind of searches that can be done. And there is an amazing improvement in particular in the statistical analysis that can be done experimentally. So here is what the two experiment Atlas and CMS have come up with, and it's pretty amazing. So the plots that I show to you here that are from Atlas and CMS, they show you what they expected they will be able to do with a few inverse femtobars. So on this plot from CMS, you see exactly the same exclusion limit that we saw for the Tevatron, expected, of course, because the data are coming in, but they have not been combined yet and analyzed in full, and we don't have yet 1 or 2 or 5 inverse femtobars. But if the machine keeps going the way it's going, we may have them by the end of next year, right? By the time that the LHC shuts down for a long break. So this is becoming real. And here you see curves for 1, 2, and 5 inverse femtobars at 7 TeV, the current energy. And they also played around with the idea of going to 8 TeV, although it doesn't seem to happen. But let's stay with the one at 7 TeV. So what you see here is just that even with one inverse femtobar, you'll be able to check the Tevatron, you see, and do a little bit more up here. And by the time you get to 2 or 5 TeV, you're almost able to exclude the entire mass region up to 500 GeV. So it's really amazing what by next year we will be able to do. So by next TASI, the talk on Higgs physics will be completely different, right? So this is amazing if you think through, right? So it's the first time in my lifetime, in my scientific lifetime, that this happens, right? So you are starting with a bang, really. So If the atlas plot rephrase mainly the same thing in a slightly different way, giving you the significance, so how many sigma they expect to have for discovery, and here they're plotted. And this is given for a larger, so for 5 inverse Van't in blue at the 2 energies, and for 10 inverse Van't, so with the much higher statistics for this very same 2 energies. Here is the exclusion limit of the tevatron. Right, and here is what you expect to reach with the two different luminosities. So let's say with the lower one, well, they're there, right? So they can definitely, even in difficult mass region, they can definitely reach this exclusion and discovery. So you can get, as I say here, 5 sigma significance for a standard model Higgs in the 140, 170 mass region, which is the really crucial one. Now, meanwhile, for these particular searches, the main modes that have been used are the ones that are listed over here. So they are Higgs, inclusive production of Higgs, with Higgs decaying into WW and ZZ and gamma gamma. But other studies are ongoing to use the decay for BB bar and tau tau with new idea, like looking at different kinematic regimes where the Higgs is boosted, for instance, in such a way that you can use the boosted structure of jets. So there are many nice ideas out there to improve your reach and to stretch your reach. And there are data. So when you see this plot, you feel good because the dots is not Monte Carlo anymore. They're data, right? So it's just amazing that finally this is all coming in. And I'm sure you will hear more from these 2 lecturers during this school. So now we need to see how a theorist can do a good job, right? In telling experimentalists what do we expect in the standard model. So this is a very elementary and basic cartoon of how we picture in our mind, in a simplistic way, a hadronic interaction. But it has a lot of information that saves me a lot of time in putting all these formulas down, and it just gets to the main, to the core of the matter. So here, if you imagine your proton and antiproton, and your proton or proton coming in, and in there you have partons. The partons are distributed with some distribution functions, parton distribution functions in the proton and antiproton, or in the 2 protons of the LHC. They collide, and the core of your prediction at the collision is what we call the hard cross-section of the parton level cross-section. Now, from here on, what comes out starts radiating partons. The energy goes down, and you get to the hadronization scales. From here on, so from the point in which partons come out from the hard cross-section, you use typically to simulate the showering of partons, of the hard partons that are coming out of the main collision, what we call parton shower Monte Carlos, that are mainly based on the main properties of QCD, so on the property of parton emissions in QCD. So they're not just far-fetched, right? But they are just based on the best use of QCD that we can have in order to simulate these kind of very complicated dynamics. And down here at the hadronization, you have modeled to simulate the hadronization. So this part here is what you typically do with objects like Pythia or Horologium. Now, the 3 fundamental stages in your mind should be the initial one, in which you specify how partons are distributed into hadrons, so the parton distribution functions. Those have a non-perturbative core, and they are evolved perturbatively to the scale of your collision, right? So there is a part that is non-perturbative, that is just fitted from experiment, and that non-perturbative core is then evolved in a way that you control perturbatively, which is the evolution via the Altarelli-Parisi equation. So when you get to when you finally have your partons at a scale, let's say, that you then wanted to vary to study the dependence on that scale, but at the scale of the hard cross-section, this is where you do your calculation in perturbative QCD of the cross-section at the parton level, and perturbatively including all the orders that you can, or that is reasonable to include. And this is the calculation of sigma hard. And then you interface that with parton shower. The interface typically has always been done at tree level, but we will see that a big improvement has come from the ability and the capability of doing this interface a step forward. So by the time this hard cross-section is calculated, the next to leading order. And therefore you have a chance to have modeled the hard interaction much better than not at tree level. And we will discuss why. So schematically, just to put it down in words and in formulas what was on the previous transparencies. The hard cross-section is calculated perturbatively, as I just said. It starts at a given order, that here I denote by alpha s to the k, and you add to that the following orders by going up in the perturbative order, loop by loop, radiation by radiation. So we call the n equal 1 in here leading order, so the one that starts at the lowest order in alpha s, the n equal 1, the n equal 0, the n equal 1 next to leading order, and so on and so forth, just to set the terminology of what comes later. Now, it's convoluted with initial state parton density at the same order. You have to be consistent in your order of, so use leading order with leading order, next to leading order with next to leading order, and NLO with NLO, and so on and so forth. And then there is hidden in this formula is scale dependence. So there is hidden in this formula the fact that you are not calculating an exact cross-section. You're calculating a truncated cross-section, perturbative expansions. And there is therefore a dependence, a leftover dependence on an unphysical scale, or actually two unphysical scale. One that is the renormalization scale in sigma hard, and the other that is the factorization scale, that is the scale at which you interface with the PDFs. And because both objects are truncated, there is this leftover scale dependence. The overall physical cross-section, of course, does not depend on that, but you don't have it theoretically. That's a problem. So if you set them equal for simplicity in writing, not to have too many things to write in just one line, this is how you should look at the formula that we had on the previous transparency schematically. So this is the convolution with the PDF. There is a scale dependence in the PDF that is both mu f and mu r. And there is a scale dependence in the cross-section that is both mu f and mu r. And there is a scale dependence in alpha s that is mu r. Okay? Now, the systematic error comes from the PDFs. The theoretical systematic error comes from the PDFs. It comes from alpha strong, how alpha strong is the error that we have in the determination of alpha strong. And then from the leftover scale dependence that comes from it's in the PDF also, but if you take into account this error into the PDF error, it would be the scale dependence of your cross-section here, or the convoluted cross-section. And then input parameters. Your cross-section may depend on input parameters, masses, couplings, and you may have an error on that. Typically, this is very, very small, unless you get to processes that involve maybe a B quark, and you can have an error from the B mass. But it's still very, very small compared to the others. So sometimes it's not even considered in giving the error from the theoretical cross-section. So here we come to the first item in the theoretical system, in the systematic theoretical errors that we have. So the error from PDF, you need to be very careful here, right? And the reason why you need to be very careful is just it's very hard to quantify the error from PDFs. And where is the error coming from? Well, this set, as I said, they have a non-perturbative core and they are evolved perturbatively and they are fitted to data, right? Because you don't know the non-perturbative core, so you have to fit to data. Now, the fit, therefore, depends on the input measurement that you put in, so which data you compare to, they have an error, of course. But it depends also on the way you model your fit, so it depends on the parameterization of your fit. And at the moment, we have many, many sets of PDF, 3 of which are built fitting on collider data, and therefore we want definitely to consider every time we have to make collider predictions. And those are this set that you may have heard of, that has the CTAC, the MSTW, and then the neural network PDF, and NPDF. Now, the error that comes from the input parameter is easy to estimate, and each set provides you a way to do that. So what they do, they provide you with a whole bunch of replicas, if you want, of a given set of PDF, let's say CTAC or MSTW, spread out when the input parameters are varied over their errors. And so you iterate, you calculate your cross-section over these 40 or 30 or 50 sets of PDFs that you have, and statistically you calculate the deviation that you have, and you calculate your theoretical error. But this is, yes?
Does anybody other than NNPDF do that?
Say it again.
Does anybody other than NNPDF do that? CTAC normally just gives you an error bar. You're supposed to propagate it through yourself.
CTAC allows you to calculate the internal, what I'm talking about right now.
I thought only NNPDF gives you actually a set of PDFs.
No. Also CTAC and MSTW, they do, yeah. So, but then on top of that, which is normally not big, so it's normally of the order of 3–4%, that's what you get from spreading it within one single set. On top of that, you also have the difference between sets. And typically what happens is just that if you calculate something with different sets, the difference of the central values is much bigger than the internal error of each set. So you calculate something with CTEC or with MSTW, and you find the difference between the two central values. So the values that you get, the result that you get with the central values of one and the other, to be much not within the internal errors of the two sets. So that's a worry. Right? So that's the fact of saying, then what is the real meaning? What should I do? Right? Because they're all built out of collider data. And that difference comes from the difference in the parametrizations. And it's a difference that is maybe not there over the entire range of x's, but in some parts of the range of x. And so you need to be careful about that. And typically, there are very conservative and less conservative approaches. There are people that think, oh, I know that this is the right set to use and just go with that. But if you have to do an experimental, if you have to really to set an experimental bound like the tevatron, you've got to be careful with that. And so what was done actually by the tevatron is something that is also now done at the LHC, and I think very reasonable, and it's just to use the three sets and to build what is called the envelope of the error. So take, in a way, there is a formula for that, but what it is just to take the maximum of one and the minimum, the maximum of the maximum and the minimum of the minima, and your central value is in between, and that is the band, to say it in few words, right? Now, the criticism, one of the criticisms to the experimental measurement of the tevatron has been that that uncertainty had been underestimated because other sets of PDF had been left out. So set of PDFs like ABKM or HERA PDF. These are PDFs that are mainly based on GIS data or HERA data. And the rationale for the tevatron to leave them out was just that they were not based just on collider data. And so that's why they didn't use it. If you start using them, as you see in this plot taken by this paper, that is the paper where the main criticism came from, you see that there is a big spread because, well, you see in here MSTW is the black curve, and if you use one of the HERA PDFs, is down here. So it's a huge difference in the cross-section. And so if you come in terms of uncertainty, you see that the blue band is what was used by the tevatron exclusion measurement. And if you relax your acceptance of possible PDF sets and use other PDF sets too, your band becomes much broader. Now, the result is obvious, right? Because you just allow for more theoretical uncertainty and you are less predictive experimentally. So your exclusion limit just goes up. So all those curves that you see in the previous plot, boom, bump up. And at that point, you're not excluding anything anymore because you don't have precision enough to do that. So you don't know well enough of the theoretical uncertainty to do that. But the criticism back from the experiment is, as I said, the experiment didn't work in isolation. It worked with other theorists that confirmed the fact that it was reasonable to use the three sets of PDFs written here, but one should not really be over-conservative using also sets of PDF that did not include collider data. And for that reason, the experiment stand on it with the measurement that they just given, with the exclusion limit that they just gave. However, I would take these as an indication of the fact that you've got to be careful there. And this is precisely what has been done now at the LHC. So the LHC is now working at providing the best theoretical estimate for all the production mode combined with decay modes that we have and we are going to use at the LHC. And of course, the issues PDF, it's a big issue. And what you see here is a plot that comes of the main study that has been done during the last year of cross-sections for the LHC and has been published separately in this paper. And it shows you over a broad range of axes, so over a broad range of square root of the partonic cross-section over the hadronic cross-section, so basically products of x's. It shows you over in this plot different sets of PDFs, including the three collider data-based set that we had before, MSTW, CTEC, and an MPDF, and also including HERA PDF that, as you see, doesn't get over the entire range. But in here you see that there is a range in which within their error bands they're all compatible, and there are regions in which they deviate a lot. So you cannot just use one or the other. You have to take the envelope of both. You have. That's a suggestion if you want to be conservative. And this is what the envelope is. So unfortunately, you cannot see the green very well. But if you saw the three bands, you would see that the PDF for LHC recipe is precisely the envelope I've been talking about. And you will see that the black curve just convolute them all, envelope them all. So you just include all the bands with an average that is just the average between the maximum of the maximum and the minimum of the minimum. So there is another point that we don't have NNLO PDF for all three of them. So only one set, which is MSTW, provide NNLO PDF. So if you have a process that you have to calculate at that order in order to get a stable hard cross-section, that's the only option you have. And so what has been suggested is just that the error that you get at NLO is just rescaled by the difference that you see within MSTW between NLO and NNLO, because that's the best you can do and it's pretty conservative. Otherwise, you wouldn't know how to estimate an error between different sets. You would know how to estimate an error within one set. Now, let's come to the next big building block, the hard cross-section. So the hard cross-section is what you calculate perturbatively in QCD. You calculate perturbatively in QCD, and then, as I said, well, you can push up the loop order. Let's call it these ways. You can push up the perturbative order. Why to do that? Why do you want to do that? Well, there are many good reasons, and here are the most important ones. So the first one, as you know, scale dependence. So the scale dependence is an artifact of the fact that you have a perturbative calculation that is truncated. So if you truncate a given order, the scale dependence normally is pushed up to the next order. So the error you have, the residual dependence, should be less, right? Unless other things happen. And other things that may happen is just that at the next order, new channels open up. And these new channels that open up at the next order, they are actually tree-level when they open up, so they have a strong scale dependence. And therefore, this is a recipe that can already give you the results at the first order, or you may need to push one order further if your process has a kinematic or as a structure that is particular, right? So you really have to look at the structure of the process. But as a recipe, you need to add perturbative orders to get the scale control, to get the scale dependence better or under control. And this is systematic. It can be systematic. And the thing is just that when you see that these dependencies behave well, so it goes down order by order, then you have the systematic of this error under control. When you see that this is not happening, you need to explore more in order to understand what's going on, right? Is this due to new channels opening up? Is this due to what, right? And when you understand that, then you become systematic in your error. Now, the physics richness is the second point, and I have already said something that goes to the extent of the physics rich. New channels opening up and next to leading order, or next to leading order. Normally it happens at the first order. It doesn't keep happening, right? And this is crucial. It is crucial to have under control the systematic of your process. It is crucial to the next step, to the step that interfaces with pattern showers. So the farther you push in energy your interface with the next step, the more structure you have under control in QCD, because you have calculated it. And there is less left to an approximation of QCD, which is the showering, which is based on the fact that hard radiation and strong radiation mainly happen in a collinear regime, right? So the more, if you wanted to calculate a process that has hard patterns in it, hard jets in it, you cannot think of calculating it with a pattern shower because you will not get the hard radiation. So the more you push at the core level, at the hard level, the more final state particle you have at the hard level, the better you are in modeling a process. So this is important. Now, the last step is the final interface, what I was talking about, the interface with pattern showers. And this is, it is important to push the perturbative order further to make that interface more meaningful. And it is important also for another reason, that sometimes to push the loop order higher. It is important because in the perturbative expansion, you may have that everything is well ordered in terms of alpha strong, but it may also happen that your process is such that there are multiple mass scales in your process, or there are particular kinematic regions in your process that are particularly important, such that large logarithms appear in your calculation at each order, and the perturbative resummation is not necessarily well done in alpha s, but is done in alpha s log or alpha s to the n log to the m, depending on the order in which your process starts. So in order to have that resummation better under control, in order to understand it better, it's good if you can push your calculation higher in order, higher in perturbative order, a fixed order. So we will see all these with an example, which is precisely the gluon-gluon fusion to Higgs production, because that's why I think it's a tutorial, because it contains all of these. So all of these considerations will become clear from the results that I will show you. So this is just for your reference. I don't want to go over all this, but I want just to show you, to tell you that the NLO challenge, which means to take all the NLO processes that we need for Higgs physics, as well as for many other things, and have them under control, has been the main goal of the QCD community for the past 10 years at least, right? And the progress today is enormous, has been really great, to the point that it has almost been automatized, meaning that you don't really need to do it with your own code anymore if you don't want. It's not completely done yet, but we have now automated code that I list you for your reference. So when you go back to your notes and say, oh, what was the name of that thing? Just to look it up, right? So here are packages that can do virtual correction in an automated way. So you give a process and you get the virtual correction. They're not there for you yet, but they will. So for the moment, the results are just from the authors, but they will be public. There are processes that give you the real corrections, and one of which you probably already know very well, which is MADGRAPH, because you also use it for leading order kind of calculation. But now both the real radiation and the virtual radiation in the version that is now known under MADLOOP had been implemented. It's still in a testing phase, but it's going to be there by the end of the year. And there are codes, there are environment and packages that do the interface of an NLO calculation with a Parton shower for you. So in a way, the NLO has been considered and is considered a solved problem. So something for which we do have the tools that we need. And this is great progress. This is extremely important when the LHC is finally ramping up and working. So it's great that our community has been able to do that. Now, you may be asking, when is NLO not enough, when I need to be higher order? Well, there are situations in which this happens. So situations in which you need to have the perturbative structure of your process. The perturbative structure of your process is a little bit special. Maybe it starts with a very, very low multiplicity in the final state. And to get the real structure of the real hard emission structure, you need to push up, in particular, the real part of the emission to a higher order. And then the virtual part has to come along. And this is precisely the case of gluon-gluon fusion, because gluon-gluon fusion produces one Higgs. So it's a 2-to-1 process. So you're not going to see something like that in your collider. In your collider, you're going to see something produced with a lot of jets and things. So you need to be able to disentangle both the signal and know the signal as well as the background that is a multi-jet thing very well. So in those situations, you may need to push the perturbative order higher. Or maybe when the precision or determination of the error is so crucial and is so necessary that you need to have numerically that kind of precision. Now, along this way, there are important questions that arise, and I don't want to address them all, but I listed them because if you ever happen to be in a discussion about collider physics, about a particular process, you'll hear this question coming up typically from experimentalists over and over and over. And, you read through them, so I just pick some of them. Should this factorization randomization scale be varied separately or together? Or other? I don't know, how to deal with higher order differential distributions, or what is the impact of jet vetoing on our NLO calculation, or on the theoretical calculation? They're all very legitimate questions. They don't necessarily not have a unique answer. Sometimes it's process dependent, but there are some guiding principles that you can follow. And the guiding principles that I list for you here are very, very general, but very, very strong at the same time. So one thing that you want to have for your theoretical prediction to look good is that the dependence on their physical scale is reduced. And this may take various considerations. It may take the consideration of just simply adding perturbative order, or choosing the right expansion parameter, that may not, or choosing the right scale range. Because sometimes, for instance, when you do jet physics, it's not clear at all what is the scale that you have to use as central scale about which to vary. But you may just be choosing the wrong scale and therefore introducing spurious large logarithm in your calculation. It's just taking a series and not resumming it well. So you don't get a reasonable result, right? So just because you pick just a little bit of it, that's a problem as well, right? So this is a very important guiding principle that case by case has to be addressed. So the other thing that you want to, how to achieve this fundamental, these two considerations just boil down to what I just said in words. So how to achieve this, there are many possible steps that you have to inspect. And some of them I have already mentioned, so add corrections, or choose the best expansion parameter, or just look at the possibility of resumming part of the corrections and over and over and over. And the tutorial example that we are going to see is going to address all these points. So here it is. So you know already the structure of this process because we have discussed the decay. So we have discussed Higgs into glue-glue. So it's exactly the same as far as the analytical expression of the starting point. So here is your diagram at the, let's call it 3 levels. So it's the lowest order. So here is your lowest order diagram, which is the loop diagram. But you can, as we discussed for the decay, address it in an effective theory in which the loop of top quarks, which is the only contributing one, basically, is squeezed to a point in this effective theory. So this is your fundamental vertex. You can describe this vertex in a Lagrangian that has this form. This is the coefficient then you calculate at higher order in QCD. So this, in an effective Lagrangian language, this is precisely the coefficient that is calculated at higher order in QCD. So you will have to address the renormalization of this coefficient and the normalization of this operator at higher order in QCD. Now, when you include an NLO and an NLO QCD correction, this is the results that you get. Now, let's look at the plots. So we don't go through the calculation. The calculation has been done. If you're interested in how the calculation is done, you had seen some of the plot. It's very similar to the calculation of the decay, except for some complication due to the hadronic, to the fact that you have an hadronic state here in the initial state. And you are radiating it as well as correcting it through loops. But you have seen some of the diagrams already when we showed the decay. You know what is behind it. So it's just 2 more QCD interacting objects attached to the fundamental vertex of your calculation. Here are the results. And this is what I want to discuss with you because it addresses one of the points of, let's answer the question of what is the, it addresses the point, and it comes to the point of just having the scale dependence of your prediction under control. Okay, you do the calculation, you do it, so here is the Tevatron, here is the LHC for 2 reference energies. So here is given the Higgs mass range over which the study has been done. You can push it forward for the LHC, but it doesn't really pay. So let's look at the characteristics. The black dot curves are the leading order. The green dash curve is the next to leading order. The red solid curve is the next to leading order. And what do we notice both left and right is, first observation, the leading order and the next to leading order bands that have been obtained varying the scale within a factor or 2 about the central values of M Higgs, which is completely arbitrary, but it just gives you an indication because we want just to compare one order with the next with the next. So let's look at when we vary within about that range by a factor of 2 down and up, what do we see? We see that the leading order band does not overlap with the next to leading order band, right? And the scale dependence is mildly reduced, but not much. So the 2 things that we see is just that there is not a huge gain in scale dependence, but the most worrisome part of the 2 is just that they're so different one from the other. So that when you go from the leading order to the next to leading order, you have a huge jump up. So it looks like it's not perturbative at all. So it looks like your series is just going to give you crazy numbers the higher you go in the expansion. And you have it on, this is definitely not systematic. So you cannot estimate a systematic theoretical error for something that has a correction of 100% at the first order. This is specifically a case in which you want to go NNLO to understand something. And if you see the same thing, well, then you don't understand really what is happening. But maybe not. And in fact, you don't see the same thing. But when you go to the next leading order, you see the behavior that you would like to see. So you see that the scale dependence, which is the width of the band, is much smaller because the band is narrower. And there is overlap with the lowest order, so with the NLO. So now you take you're kind of relieved and they say, okay, the perturbative expansion starts working, right? It just took 1 more order to start. And the reason for that is just that the process is so special. It's a 2-to-1 process with a gluon initial state. So you expect in any case that the QCD correction to be very important because you have a hadronic initial state made of gluons where the radiation is really important. And there is a lot of, it is dominated by collinear and soft effect in particular. So as soon as you start having radiation, you have a big logarithm coming in. And you expect the structure of the process to be much richer, just 1 order up, because you had 1 parton in the final state that was not there before. And so it's as if the whole QCD properties of this process, they really start at NNLO. And from there on, the series starts converging. And you really see it both at one machine and the other machine, to the point that when you look at your precision, the precision at first, when you go from NLO to NLO, you still have, with an effect of 70%, you cannot really estimate the error. Yeah, you can look at the scale dependence, but what is the scale dependence really telling you if you don't even see, if you are off by 70% from the leading order? It doesn't tell you much, right? So you have, by the end, however, so by the time you are at NLO, you have a residual theoretical uncertainty that is now systematic because you now understand what's going on, of 15%. Now, you can understand even better, and you can understand even better precisely if you look now at the characteristics of this process. That is a process in which, as I just said, real radiation, in particular soft radiation, is very important. Why is that? Well, because you are producing a very heavy object, so at a given energy, and this is particularly true for the tevatron, there is very little left over for something else. Right? So there is very little left over for extra radiation. So it's preferentially emitted in a soft region. That's why. So this is particularly true for the tevatron, and this is why I show this plot for the tevatron, but it's also true to some extent for the LHC. And we know how to resum from randomization group argument. We know how to resum, and with the due formalism, this kind of radiation into resummation factors that take into account the bulk of the soft radiation at a given order, like a leading logarithm or next to leading logarithm, and so on and so forth. This is a resummation of term of the form alpha s to the n log to the m, right, with n and m specified by the leading log, next to leading log, and so on and so forth. And so when we so do, this is an example of what happens. This is the NNLO prediction, so the red band that we had on the previous plot. And the blue is how this changes if we add to that also the resummation of the next to leading logarithm of the soft radiation. That is, of course, particularly important in a certain region more than others. So the scale dependence, as you see, the central value goes up and the scale dependence goes down. So we get a better theoretical prediction. And so we go from a 15% uncertainty to an overall 10% uncertainty from scale dependence, to which we need, however, to add the uncertainty that is still coming from the PDF, that is always lurking there in the back. And we have discussed that a few transparencies ago, and it needs to be added to this one in a way that is always under discussion. Should we add it in quadratures? Should we add it linearly? So these are further kind of worries that you may have at a later stage. And remember that this is important because there was a time, for instance, a couple of years ago, when all of a sudden the predictions went up or down by a whole lot because the set of PDF that was used was changed. So there is a real issue there that needs to be addressed. And this has been taken into account in the prediction that are nowadays given to the LHC in order to use in Higgs searches. Other kind of resummation that goes into this prediction is for distributions. When you look at distribution, so for instance, when you look at distribution with the transfer momentum of the Higgs, for instance, you also have to be more careful because, of course, a distribution may point out to regions of kinematic. Yes?
Maybe I'm not allowed to ask questions.
No, you are.
If you look at the previous slide,
Yes.
I didn't, so how do I know when I do a calculation whether estimating the uncertainty by scale variation is a reasonable or not a reasonable way of accounting?
Well, yes, that's a good thing. Okay, let's go back to this plot. That probably it answers the question. Yeah, one of the questions, for instance, and one of the issues that was made, for instance, for the tevatron measurement was just that they had considered a variation of the scale by a factor of 2, but actually, because of the uncertainty on this process, they could also consider a factor of 3, right? Or something like that. So he's asking, how do I know how much I have to vary the scale? Well, yes, in this plot, for instance, I could have varied the scale by a factor of 3. Right? And what I would have seen probably that by then the leading order and the next to leading order, they would have overlapped, right? And the band would just have grown bigger, so of course I would have started seeing some overlap with all of them. I can go to a factor of 4 and they will all overlap, right? But when I look at something like this, of course, if I don't have the NNLO, I have no real way of saying it. But if I have the NNLO, then I see that I don't really need to do that. Right? So what I have the NNLO, what I see is just that varying by a given amount, that here is 2 by a factor of 2, I do see overlap between the two. And so here I understand what is going on with the perturbative expansion, and I don't need, it's all a factor of saying how much conservative should I be, right? And here I see that I don't need to be more conservative than what I've done, Because yes, I mean, it doesn't really pay to add theoretical error if you don't think that is really somehow needed to describe the physics of the problem. And here is not needed more than that, which I know in retrospecting after having had the NNLO. Before having the NNLO, I wouldn't know. I mean, the thing that you should do is just actually to enlarge your factor in order to have overlap between the leading order and the next to leading order. And so I should use a much more conservative error. But at the same time, it would be worrisome. I don't know how much to really, what the meaning of that would be when you see that the impact of the correction is 70%, right? So that is what really worries you, more than even how much the scale variation is. So you really can say something only if you go up one order. And at that point, you try to use what is reasonable in order to describe, in order to show what is the reasonable amount of variation that allows you to show the behavior, the correct behavior of the perturbative expansion. So let's go to here. Okay, so resummation in distributions. Yes, what you see here is the distribution in the PT of the Higgs. So, of course, this is something that happens only when you go higher order in QCD because you don't have it in a 2-to-1 process. You need something else in order for the Higgs to have a PT, right? So this is a purely QCD effect, is induced by radiation. Now, in these plots, you see what you obtain when you have a fixed order calculation like this one, where the LO here is just the first order in which you can even calculate the PT of the Higgs. So it's already the NLO, the fixed order calculation. And here is what you obtain when you resum large logarithm that appear in the distribution that are logarithm of the PT of the Higgs over the mass of the Higgs that are written right here. So this calculation, the way they're done by resumming these large logs in the low QT mass, in the low QT region, so for low PTs. And they are done by fitting to the fixed order calculation in the large PT region that is over here. And this is what is used to compare to experiment. And this is what gives you the distribution on the exclusive part. So the distribution on the differential cross-section of the order of 15-20% or 8-20% when we go one order higher. So another kind of study that goes along the line of looking at the behavior of your perturbative distribution. Now, the Higgs is really looked at in both production and decay, as we have discussed from slide number 1. So you should really look at the full thing, not just the production mechanism, but the Higgs produced and decaying, and to look at how it behaves, therefore, in what we call the exclusive channels. So the channels that do not just produce the Higgs, but then decay the Higgs into some final product. And for this particular process, so for gluon-gluon fusion, the effect of higher order QCD corrections to this order has been studied and implemented actually in 2 codes that are listed here for the Higgs decaying into gamma-gamma, into WW, and into ZZ. And this is what used by the Tevatron and the LHC. And the effect of the corrections are clear here, where on one side you see something similar to what we saw already for the inclusive cross-section, so the non-overlap with the leading order, but overlap with the NNLO when I keep the same variation around M Higgs by a factor of 2, so the convergence of the perturbative series. But the amount of the effect of the NNLO varies greatly when you shift, for instance, from one value of the mass of the Higgs to another value of the mass of the Higgs, and here you see a distribution in rapidity as a matter of fact. So you see that in one case you have a big enhancement of the cross-section, in the other case the 2 bands are completely overlap one with the other. So this is to tell you that when you look at distributions, you cannot guess the effect that NLO or NNLO correction or QCD correction have on distribution from the effect that they have on the inclusive cross-section. So the famous rescaling by what generally is called a K factor, that is the ratio between NLO and LO, or NNLO and NLO, right? So this rescaling overall over the entire range of a distribution is not a safe thing. And this is what shows you that, because you look at different situations and the effect of the corrections is completely different from one case to the other at the distribution level, not at the level of the cross-section, of the inclusive cross-section. Not to talk about the fact that on top of looking at the distribution, you may also experimentally need to put cuts on certain kinematic variables. So you may need, or you may need even worse, to exclude a certain final state particle from your measurement, what we call a jet veto. So exclude maybe jets with a PT higher than a certain amount, or things like that. That completely messes up your QCD prediction, theoretically. Because you see, theoretically, a pattern that you have in your calculation may be needed in order to have the consistent infrared structure of your prediction, because you need that object. And now all of a sudden, experimentally, that object is excluded. So you really need to study precisely what is the effect of the experimental cuts on your theoretical prediction before you can give a number. And this has been done already for this channel, and I wanted to show you some results over here that are probably difficult to read, but I will guide your reading. So this is for gluon-gluon fusion, again, with the Higgs decay into WW, and the decay pushed farther to the decay of the W into leptons. Fortunately, this is really what you need to do, because this is how the two Ws will look in the experiment, and this is really what the experimentalists do. And the cuts that they put, they are cuts on the leptons that are coming out, or the missing ET, right? So unfortunately, you have to go all this way down to be able to compare with experiments. So you need really then to go the way back and see what you do down here. What is the effect of what you do down here on your theoretical prediction of this cross-section? Does it make sense? What are the effects of QCD correction by the time you have done all those cuts? They may not just be guessed, they have to be calculated, right? And here you see it. So the cuts that are imposed here are precisely a jet veto and a separation cut between the two leptons. So experimentalists tell you what is the best way to see this signal. And they tell you you have to just forbid jets with this given PT, and you have to allow this given separation between the two leptons, not more than that. And that's what you do theoretically. You just build the distribution of your cross-section as a function of those two observables on which experimentalists are going to cut. Right? And here is what you see before you really, and here is what you see when you put that, when you look at that cut, those two cuts in place with different values of the cuts. Well, you see very different behavior, as you see. You see that the relative behavior on top of the general thing, so the fact that, again, you go up a lot from leading order to next to leading order, a little bit less than next to leading order, but the real numbers and the way the things overlaps one or the other is very different. And here you see it even better. So here you see the K factor. You see what the K factor is the ratio between N and LO and LO. So the ratio between the fully corrected object and what you started from, okay? And here is by now, in many plots, we always see bands, and those bands is just due to the variation with the scale. So it's just the whole spectrum of things or results you can get by varying the scale within that factor of 2. So you see that the band with cuts, let's say that is, just look at the red ones, which is the N and LO. The bands with cuts is this one, and this straight one that I put here is the one that you would obtain just from without cuts. So the one that you would obtain just from the non-cut and the inclusive, if you want, cross-section, the one that hasn't taken into account the decay. So you see a completely different behavior. So this is precisely what you want to take into account, the kind of work you need to do in order to answer the question, how can a theorist do a good job? And final step, just because everything has been done basically for this mode, because it's so important, it has been interfaced with NLO Monte Carlos. So it has been interfaced at NLO with parton showering. So the interface with parton showers have been pushed that farther order up or down, depending on what you want to look at. And the problem here, if you are thinking about it, is just that, well, we said that the calculation was done at fixed order and with resummations up to NNLO and the next to next level of logarithm. But these are NLO Monte Carlo. So we don't have NNLO Monte Carlos yet, right? So we cannot interface an NNLO calculation with the Monte Carlo. So what has been done here is just they have taken a step back in the perturbative calculation and use the NLO part of the calculation, as a matter of fact, interfaced that properly with the parton showering according to either the MC at NLO or POWEG prescription that have all the right subtractions in such a way not to have double counting. Because as you may imagine, in the NLO calculation, you have already part of the real radiation in, and part of that radiation is also in the parton shower, at the first order of the parton shower. So you need to take into account that you have a double counting and to subtract it properly. So all that has been done in NLO. And then the curve will be used rescaled by the amount that goes from the blue, which is the NLO and NL result interface with the Monte Carlo, to the green, which is the result of the full NNLO next to leading logarithm calculation perturbative calculation with no showering. So basically, you estimate the effect of the interface with the showering at NLO, and you rescale your result at NLO by that effect. That's as good as it can be these days. Yes?
Can you go to the previous slide?
Yes.
In your K-factor plot on the upper right corner, why is the scale of uncertainties in the NNLO bigger than that of the NLO?
Well, that's the thing, because cats can play that funny thing. Because you are excluding, you're cutting on various regions of the parameter space, of the kinematic space, and you may be messing up a little bit with the perturbatives. This is actually something that is interesting to see, because when you see something like this happening, it brings the discussion to, should we really use those cuts? Because the theoretical prediction becomes less certain, as you just noticed, and it's a very good point, actually, right? So what you're saying is, well, on this side, I see something opposite than that side. So on this side, I see that the band is shrinking, but now when I well, sorry, I'm confused. No.
Ruining the convergence of the perturbative expansion like that, or aren't you? It seems like you're messing something up when you're.
Well, no, not really, I would say. Part of the effect is due to the cuts, as I was saying. But still, even when you see something like this, that you can justify by that. So the effect, well, first of all, you have to look at, this is the K-factor, so it's the ratio between the higher order and the lower order, right? So it just tells you that in this region, the effect of the NNLO correction with respect to what you started from are larger than in this region. And this can be, right? So this doesn't even have anything to do with the cuts. So I was answering to, actually, I misunderstood your question. So I was answering a different question. But let's address the point. So this is a K-factor. So it's the impact of the highest order correction over the tree level. So it's telling you that down here, for this value of the cut, you have a smaller impact than up here for a higher value of the cut. That could be. And it could be different from what you see at NLO. But it's not a signal of the fact that anything is going wrong if it's compatible with the NLO, and if the overall the prediction that you're looking at is basically consistent with the previous order, which is the NLO order. So it's true. You say the NLO factor here has a less impact than the NNLO factor, but that doesn't really mean this is the K factor. So it's a ratio between the two. So it doesn't really mean that there is anything going wrong with your perturbative expansion. What you really see. What you should what is more indicative is what you see on this side, where you see the full scale dependence and the behavior of the overlap. So in a way, what you're seeing on this side is just that here the two starts overlapping a little bit less. That's what you're seeing over here, right?
Could I interpret the increase in the scale dependence because you're dividing by the leading order, which also has a larger scale dependence?
Yes.
And the next to leading order, the blue band, might have a similar sort of scale dependence as a leading order.
Yeah.
So when you take the ratio, the scale dependence
Right.
is artificially.
It's also artificially small. That's a really good point too. I mean, if you look at this plot, he's saying if I take the ratio of these over that, so if I take the ratio of the NNLO over the LO, that both have large scale dependencies, is artificially small. But now I'm taking the ratio between the NNLO and the LO, and so this becomes big, the ratio, because the mu dependence of the ratio is induced by the denominator, not by the numerator. That's another important point, which is also the reason why K-factor are not really nice objects to use, right? So yes.
Right, so quick question.
Yes.
So on the next slide, with the you're talking about the NCE at NLO.
Yes.
So this is still matching onto a leading log part of
Yes.
it, right?
Yes.
So is there any is there a need then to develop a next leading log Parkland child or is it possible?
It is possible, right? It's even done in certain cases, but it's not completely there yet, right? So, but it is possible, and I think you're going to have. I think that like the lectures of John Campbell starting this week, they will address NLO Monte Carlo, so they will surely touch on this topic and give you more details on that. So to wrap up our discussion, I want to show you what you can do if you do the same kind of thorough job on all the processes that we have seen. So you go back to the second transparencies of our lesson, and you have the 5 different production modes. You have seen what the issues are in order to predict the cross-sections for all of these, the production of all those, of the Higgs in all those channels. And you have seen in details what that boils down to for probably the most difficult mode, which is also the most important one, which is the gluon-gluon to Higgs. Now imagine to do exactly the same thing for all of them, because that's what you should do, addressing different issues. And typically, all the other modes, they do have less issues than the one that we have looked at. So they're more normal kind of production modes. They have a less special kinematic. They may have, unfortunately, they have a smaller cross sections too, but they don't present that many level of difficulties that the gluon-gluon fusion mode presented, and that's the reason why they don't also offer a tutorial, meaning that each one of them maybe address one of the aspects of the discussion that we touched together, but not all of them. But once you're done doing your homework as a theorist for all of them, and that took a really long time to the community, here is what you get. So for 2 energies that are the energies at which the LHC is running and the energy at which the LHC will get. You get these bands for each one of them. If you read it through, you see that they are the 5 modes that we discussed in the second transparencies. This is coming from the work of this working group that ran during 2010 for the inclusive cross-sections. It means just producing the Higgs, with the Higgs not decayed into anything. So it's a purely theoretical error, this one. But it gives you what is the systematic error these days. So you see large bands still for some of them. This is the log scale, so something like this is still a 10–15% error, maybe of the order of 15 more than 10. Something like this is very precise, of the order of 3–4%. And this gives you, it has been really important to have these and to give these to the experimental community, because it's all done consistently. So it means that the PDF error has been treated in the same way for all of them, that the scale dependence error has been treated in the same way for all of them. And you remember that these modes will need to be combined. And sometimes some of these modes are even background to others. So it's really, really important that they are all treated in the same way, because you can easily mess up by 1 order of magnitude otherwise. There was a question somewhere there.
Is there a good reason why these are ending, some of these are ending at 300 GeV?
Or it's just, that was just a decision where to end it, because they become so small that they're not going to be used more. And they're there, right? You can keep plotting, right? There is no reason why they stop. They don't stop there. It's just that the code was run up to there because of the fact that, I mean, when you produce heavy particles, the cross-section goes down very fast. And when you get to that level of cross-section, it was perceived like not useful to keep going, right? Okay. So now the focus has shifted on exclusive observable, because as I pointed out to you in discussing the gluon-gluon to Higgs mode, what we really need is just to go down to the final decay product of the old chain. So the Higgs will decay, and what experimentalists will do will put cuts on the decay product of the Higgs and on the decay product of the decay products of the Higgs. So we really need to do that effort. And knowing what, just wait a second, knowing what we have seen for gluon-gluon fusion, it can make a difference, and it can be important to study the effect of the experimental cuts on our theoretical prediction. And that is a really difficult kind of exercise. It is a difficult kind of exercise because, for instance, when you start taking decay of the Higgs into BB bar, for instance, the problem becomes more complicated. Or you have a process like TT bar Higgs. So then you have to decay the T. The T decays into W's and B's, and you keep going. And what are the QCD corrections to that? You should be able to calculate QCD corrections to processes that have so many parton in the final state, strong inerectly object in the final state, 1. 2, that we haven't mentioned up to now, but we should. You need to start worrying about the background if you really want it to be useful to the experimental community, because they will have to have predictions like this one, not only for the signal, but they will have predictions like this one also for the background. And the background, if you take, always have many more partons in the final state. So if you produce a Higgs, like in association with the W, and the Higgs, let's say, decay into BB bar, this is your final state for the background. So you see that immediately you are considering processes that have larger multiplicity than the process you originally started from. And so you need to be able to give the theoretical prediction for this process when the Higgs decay into BB bar. And you need to estimate how good it is to multiply the QCD-corrected production cross-section by the QCD-corrected branching ratio. Is that good enough? Can we use an arrow width approximation? Maybe yes, because when the Higgs decay into BB bar, it's in the region of an arrow width. Maybe not. I mean, we need to, in other mass region, we need to estimate that. But the background immediately has already 3 particles in the final state. So I don't need only W Higgs, but I need also W BB bar. This is a simple example, the simplest that come to my mind, right? But you go to more complicated, you go to a production mode like a T bar, and a Higgs. You go to a production mode even like the Higgs plus a given number of jets. That is what comes out from gluon to Higgs. And the background to this immediately becomes very large. Out of here, the minimum that can happen is to have a background that is TT bar, BB bar. So these are kind of processes that you need, including QCD corrections for both inclusive production, but even more for distributions, if you want to do Higgs physics. So if you wanted to be able to disentangle them, because the Higgs is not just signals, it's signals per background. The background is even more important than the signal because it's large at the Hadron Collider. So this is what is going on right now. So in a way, we have tackled the easy part, but the hard part is going. It didn't start this year, but this year we are starting putting together all the information that we have and phrasing it into a way or improving it into a way that it becomes as useful as possible to the experimental community. So to give you as a reference to you, I've listed in the transparencies there, and it will be on the slide that you can look at, where the calculations are for Higgs physics, so that if you want to look up some result or some calculation, you know who has done it, what the paper, and et cetera, et cetera. And here is precisely what I just said in Word. So what is going on the exclusive side? So obtain distributions at this level of precision, study the impact of higher order correction in the presence of cuts, and interfacing with analog Monte Carlos when the Higgs decay into the final products, and estimating the background. And for the background, I give you references here too. So if you look at here, you will see for different processes, like the one we just discussed on the blackboard, if they exist, who has done it, which kind of studies are there, and so on and so forth, just for your reference. So the disclaimer, what we haven't touched in these lectures. So what we haven't touched is a study of the Higgs properties. Okay, so if the Higgs is discovered, which is the most important issue. And that's the reason why I think that this could come next and even be skipped for the moment. So they will be next study if they see it, right? Then you really have to identify it, right? So, but if you see it, you also have to ask yourself, how do I know that I've seen it? Yes, it came out according to our prediction of production and decay, but then before you can really see something, you need to go to precision studies of its properties. So, and that means everything. The mass, you will get it, but you need to look at the is it a colorless object? What is the charge? What is the width? What is the spin? What are the couplings? The most important question is the first. All the previous question now have a very precise answer, right? So you know exactly where to look for them, and you read it through here. The couplings, it's a big issue. So how are we going to measure the couplings? And the couplings, well, it can be done at the LHC in what we call a model-independent way, so something that does not assume anything of the standard model. This kind of game in a model-independent way can be done only at a linear collider because you know a knowledge and you have an exact knowledge of the initial state energy because it's any plus any minus with a fixed energy. At the LHC, you don't know the initial energy because you just have two partons that comes with a given distribution out of the proton, right? And therefore, you cannot do a study that is just based. So at a linear collider, what you would do, you would just produce the Higgs association with the Z and then look at the recoil products of the Z. And that, since you know the energy, that tells you you can measure exactly the branching ratio, the total width of the Higgs, and from there you can determine branching ratio per branching ratio. At the LHC, you cannot do that. But you can measure ratios, and you can measure ratios in a very simple way, because if you think each measurement is a product of a cross-section and a branching ratio, and in there you have a coupling in the production, a coupling in the decay, so you measure, as a matter of fact, the product of the two gammas divided by the width, because you measure one gamma in the production, and 1 gamma divided the width and the branching ratio of the decay, right? So you get these objects out of each single channels. And as you may imagine, combining many of them with some basic assumptions, so like the gauge structure of the model that you're using, you can get to a determination of the couplings of the order of 10%, I would say. Some better, some a little bit worse, but of that order of magnitude. So it will be a pretty good job. And by the time the LHC has very high statistics, it will be, I would say, very unlikely if something has been seen and if it fits the pattern of the standard model within 10% to say that it's not what we think it is. So I leave you with some conclusions that I think are very conservative in a way, but they are true. So I think we are living these days through a new era in Higgs boson physics because it's become real, right? So we are really searching for this object, and we will be able to say yes or no, which is really important to answer the fundamental question about the electroweak symmetry breaking. There will be much more popping up at the LHC, and that will help a lot in clearing up the picture. Of course, this has become real physics, so this has become precision physics, and that's why we have spent the lecture today giving you an idea of which kind of effort has to go into the theoretical prediction if you want to do precision physics and if you want to really to say it's A and not B, right? And in the short term, clearly the effort is just on measuring all the exclusive channels and predicting all therefore the adequate exclusive observables from a theoretical point of view. On the long term, it depends on what will happen. So if something pops up, it will be studying the properties of this object, not only of the Higgs, even of something else. Or if nothing, we'll have to revisit the old discussion. Okay, thank you.